Partial derivatives. The partial derivative of f with respect to x is the derivative of f with respect to x when all other variables are treated as constant. Similarly, the partial derivative of f with respect to y is the derivative of f with respect to y with all other variables treated as constants, and so on for other variables. The partial derivatives are written partial f by partial x, or partial f, partial y, so on. The italicized d is used instead of the uppercase D to remind us that there are more than one variable and that we are holding the other variables fixed. Example, f of x and y could be x squared plus y squared. The partial derivative of f with respect to x is 2 times x, and because we treat the y squared as a constant, the derivative with respect to x is 0. Similarly, the partial derivative of f with respect to y is the derivative of x squared, which again, with respect to y, we treat as a constant, so it'll be 0, plus the derivative of y squared, which is 2y. For a more complicated example, consider f of x and y equals x squared y plus xy squared minus xy plus y. First partial derivative of f with respect to x, we start by differentiating the x squared y. Y we hold as a constant, so the derivative is going to be 2xy. For the xy squared term, differentiate x and we use the y squared as a constant. Derivative of x is 1, so we're left with y squared. Derivative of xy, again we treat y as constant, derivative of x is 1, so we get y. And because the last term, y, has no x attached to it, it's again treated as a constant, and the derivative of a constant is 0. So we end up with the first partial derivative of f with respect to x being 2xy plus y squared minus y plus 0. Similarly, if we want to find df dy, we treat all of our x's as constants. So our x squared y term, we're differentiating y while keeping x squared constant, and that derivative is going to be x squared. For our next term, we treat the x as if it were a constant, and we differentiate y squared. The derivative there is 2y, so we end up with 2xy. Our xy term, we keep our x as constant, derivative of y is 1, and for our final term, the derivative of y is just a 1. Consider the function f of x, y, and z equals x, y squared, z cubed minus xy. We want to find all of the first partial derivatives. So the first partial derivative of f with respect to x is the derivative of x leaving y squared and z cubed constant, which is y squared z cubed, and the derivative of xy, which again we're differentiating x leaving y constant, is just a negative y. The derivative of f with respect to y, we do in the same way. We leave the x alone since it's a constant, and we leave the z cubed alone since it's a constant. Derivative of y squared is 2y, and the derivative of xy, if we use x as a constant, is just going to be x. So the derivative is 2xy z cubed minus x. Finally, the derivative of f with respect to z, we treat the x and y squared as constants. Derivative of z cubed is 3z squared. So we get xy squared times 3z squared. The derivative of xy is 0. So we end up with 3x y squared z squared. Now let's go back to our question about creating speakers. Here we've changed the cost function a little bit to be 10,000 plus 20x plus 40y plus 0.1xy. What is the marginal cost of each speaker? So here we want to take the derivative of c with respect to x and the derivative of c with respect to y. The derivative of c with respect to x, we differentiate the 10,000, that derivative is 0. We differentiate the 20x with respect to x, that derivative is 20. We differentiate the 40y with respect to x. Since 40y is a constant with respect to x, that derivative is 0. We differentiate the 0.1xy with respect to x. Leaving the 0.1 and y constant, we end up with 0.1y. Similarly, we differentiate c with respect to y. The 10,000 goes away. The derivative of 20x is 0. The derivative of 40y is 40. And the derivative of 0.1xy with respect to y, holding x as a constant, is 0.1x. And to find the marginal cost at any particular level of output, say, for example, 100 Ultra Minis and 50 big stacks, we would simply plug in x equals 100 and y is equal to 50. So if we want the marginal cost of manufacturing big stacks, our y speaker, we would plug in x equals 100 and y equals 50 into dc dy. In this case, that gives us 40 plus 0.1 times 100, or $50. In addition to finding first partial derivatives, we often want to find second partial derivatives. So we'll let f of x and y be equal to x squared minus x squared y squared. Our four partial derivatives are the derivative of f with respect to x twice, the derivative of f with respect to x, then with respect to y, the derivative of f with respect to y twice, and the derivative of f with respect to y, then with respect to x. In any event, we need to find the derivative of f with respect to x and with respect to y. So the first partial derivative of f with respect to x, or f subscript x for shorthand, is 2x minus 2xy squared. And the first derivative of f with respect to y is negative 2x squared y. Now, if we're to differentiate f again, f sub x, one more time with respect to x, we get the derivative of f with respect to x. So f sub xx is the derivative with respect to x of f sub x. In this case, that's going to be 2 minus 2y squared, differentiating f sub x. If we then differentiate f sub x with respect to y, we get f sub xy, which is the derivative with respect to y of the derivative with respect to x, which is negative 4xy. If we take the derivative of f with respect to y and differentiate with respect to x, we get negative 4xy. And finally, if we take two derivatives of f with respect to y both times, we get negative 2x squared.